We've all been there. You pop open the Uber app and you just get mesmerized watching those little cars glide across the map. It looks so smooth, so perfect, like it's all happening in real time. But what's really going on behind that simple screen? Well, it's an incredible feat of engineering that's solving some massive global scale problems. So let's get into it. So here's the big question, right? How on earth does Uber manage to keep millions of drivers' phones, millions of riders' phones, and all of its own computers perfectly in sync without the whole system just collapsing? The answer is a pretty fascinating journey through some seriously clever tech. See, in the early days, Uber's system was, well, it was simple. But as they got bigger, that simplicity created a monster of a problem. Their original way of getting location updates was basically the digital version of a kid in the backseat of a car, just constantly shouting, "Are we there yet? Huh? Are we there yet?" This old method is called polling. Your app would just relentlessly ping the server over and over and over, asking, "Got new locations for me? How about now? Now?" It was a total nightmare. At one point, these requests made up a staggering 80% of all the traffic hitting Uber's servers. It was killing your phone's battery, and it made the app take forever to load. The bottom line? This just wasn't going to work long term. So, to fix this mess, Uber flipped the script. They moved from a pull system, where your app is begging for data, to a push system, where the server proactively tells your app when there's something new to see. And to do that, they built their own custom tool, and they called it Ramen. And no, not the noodles. Ramen stands for Real-time Asynchronous Messaging Network. You can think of it as a super intelligent bouncer for data. Its entire job is to decide three things. When is an update actually important enough to send? What specific piece of data does your app need? And how can it deliver that data in the most efficient way possible across millions of phones at once? So how does this whole data assembly line actually work? Well, Uber broke it down into three key services. First up, you've got a service they call Firewall. It's like a filter, listening to every single thing happening. A driver moves, a trip gets accepted, and it decides when to send an update. Once it says go, the API gateway steps in to figure out what data is needed for that specific update. And finally, the Ramen server itself bundles it all together and zaps it directly to your phone. It's this clean, super efficient process. Okay, so problem one is solved. The data is flowing nice and efficiently. But that only gets us halfway there. Now we've got a new challenge, and this one is about pure, mind-boggling scale. How do you find the 3 or 4 cars that are right near you when your database contains every single active driver on the entire planet? And I mean, we are talking about millions of drivers. They're all moving around all at the same time, beaming their location back to Uber every few seconds. Trying to find the handful of drivers in your little neighborhood is literally like trying to find a needle in a global haystack. The scale is just insane. Now, the obvious brute force way to do this would be to take your location and then just calculate the distance to every single one of those millions of drivers. But can you imagine doing that for millions of riders all at once? The system would just melt. It would create such an impossible load that the servers would crash almost instantly. It's just not an option. So instead of trying to do the impossible, Uber's engineers came up with something so much more elegant. It's a concept called spatial partitioning. Basically, they decided, hey, instead of dealing with infinite points on a map, why don't we just chop the entire world up into a grid of tiny manageable zones? Now, here's where it gets really cool. The shape they chose for that grid. Your first thought might be just use squares, right? Easy. But squares have a weird flaw. The distance from the center of a square to a neighbor on its corner is longer than the distance to a neighbor on its side. This creates a corner bias, which makes it really hard to search for things in a perfect circle around you. And that is why they landed on hexagons. A hexagon is kind of perfect. It has 6 neighbors, and every single one of them is the exact same distance from the center. This lets you do a much more accurate radius-style search. So Uber created this amazing open source system called H3 that basically covers the whole globe in a giant honeycomb of hexagons. Now, instead of calculating millions of distances, the server just has to ask a much simpler question. Hey, which drivers are in this hexagon and the 6 right next to it? Genius. And the true brilliance of H3 is that this wasn't just a one-trick pony. This hexagonal grid became the fundamental building block for so many of Uber's core features. It's used to create those dynamic surge pricing zones, to forecast demand, and even to calculate more accurate ETAs. It's one elegant solution that solved a dozen different problems at once. All right, so far we've been talking all about Uber's powerful servers. But what about the other end of the connection? What about your phone? Most of us aren't using Uber while sitting at home on perfect Wi-Fi. We're on the move, relying on cellular data that can be, spotty and slow. Uber's first line of defense against lag is something called edge servers. It's a simple idea. Instead of your phone in, say, Berlin having to send a request all the way to a server in California, it connects to a much, much closer server in Frankfurt. Just doing that can cut down the response time by over 100 milliseconds. It makes a huge difference. But, even with a server right around the corner, mobile connections can drop. GPS updates don't always show up like clockwork. So how does the app stop the car icons from just erratically jumping from point to point every time a new piece of data finally struggles through? This is where your phone itself starts to get really smart. It uses a two-part trick. The first part is a technique called dead reckoning. It's a fancy term for making an educated guess. Based on the car's last known location, its speed, and the direction it was heading, your phone starts to predict where the car should be right now, and it begins smoothly animating it along that predicted path. Of course, a prediction is just that, a guess. The final magical piece of the puzzle is a very clever math algorithm called a Kalman filter. What this does is it takes the app's predicted location and intelligently blends it with the actual location data whenever it finally arrives from the server. This algorithm is what smooths out all the bumps, gracefully correcting the car's path, and making the motion on your screen look perfectly fluid, even if your connection is terrible. Now, after all of that amazing real-world engineering, there's one last little mystery about the Uber map that people have been whispering about for years. It's the theory of phantom cars. Some people are convinced that Uber populates the map with a few fake cars that aren't really there. And why would they do that? Well, the idea is if you open the app and see a totally empty map, you might just give up and switch to a competitor. But if you see a few cars nearby, even if they're fake, it makes the area look active and might convince you to wait. Now, to be clear, Uber has officially denied that they do this, but it's a fascinating idea, right? It adds this little layer of intrigue to the whole system. The next time you're watching those cars cruise around, you might just catch yourself wondering, are they all real? And I think ultimately that's the big takeaway here. That simple, elegant map you see on your phone is anything but. It just goes to show you that in today's world, the most simple and effortless experiences are often powered by the most mind-bogglingly complex systems working perfectly just out of sight.